Today we'll learn about ALE and how you get from A to B. The problem here is hard to track. The elements are out of whack. To a simpler domain, our problem will be sent with a map that is smooth, one-to-one, and time-dependent.
So the idea is to introduce two domains. We have a physical domain that changes with time, but is hard to work with. And we have the reference domain, which is fixed in time and relatively easy to work with. So to do that, we need to introduce a mapping from the reference domain to the physical domain, and that's this mapping G. And because the physical domain depends on time, G will also depend on time. So you can see if we have a point in the reference domain, x, it maps to a point in the physical domain, little x, which is dependent on big X and on time.
The reference mesh is easily observed. The question remains, what is conserved? We start with conservation in the physical domain. Using the Reynolds transport theorem, we solve on a mesh that looks quite plain.
Consider this conservation model. We have a conserved variable u, which depends on time and space, and we have a conservative flux function that dictates the physical system. In our case, we're using the convection equation, so we have our convection velocity c and our conserved variable u, and that's our flux function. But this equation exists on the physical mesh. So this is on this goofy moving mesh, which is difficult to work with. So we can use the mapping, G or G inverse, to represent the same set of equations on the reference domain, where we can solve the equation easily. So we introduce a new variable, ux, which also depends on time and space, but reference space. And we have a new flux function. So instead of the original flux function, which is physics-based, we introduce the mapping to kind of represent the moving geometry. And we achieve this flux function here. So ignoring this for a second, we have the standard inviscid flux that we had before. So this is the convection equation. And then G inverse is the Jacobian of the inverse mapping. And little g is the determinant. So this is kind of like this flux function mapped to this domain. But to include the moving geometry, we also have to include this term, which corresponds to fluxes from the moving mesh. So again, we have the inverse Jacobian. This is the mesh velocity. And this is, again, our conserved variable. So this is kind of like a convective flux coming from the moving mesh.
In calculation of the flux, you'll quickly find lies the crux. After accounting for mesh deformation and speed, the fluxes are calculated and we proceed. Here we solve convection of a Gaussian bump and prove to you ALE is not junk. To solve the system, we use DG, like we learned in 930.
On the left is the physical mesh, which moves with time, and on the right is the reference mesh, which is fixed. Clearly, the convection equation is solved on the moving mesh, while a different set of governing equations are used on the reference mesh. All computations are performed on the reference mesh, and the solution is only mapped back to the physical mesh after the solution has been found.
There is one law ALE may break. Geometric conservation is at stake. Because the error is greater when the method is low order. Of higher order methods, we are a supporter.
Mesh, it moves. How do you do it?
With ALE, we can compute it.